This posting appeared on the AirSpy mailing list June 17, 2019. I answered to that, pointing to the significance of the selected bandwidth, and with some more comments, as you can see here. On that, there was an answer from David Eckerhart with a lot of theory. And it arrived at the ICOM is very noisy. So something is obviously very wrong. He came up with 22 dB. It means that the ICOM should be about 20 dB worse than the AirSpy, and the observation that started this thread was something the other way around. So I have to have my own look at this. I am doing measurements on this connector. At the other end there is a low noise amplifier followed by an SDR IP. First with the noise figure meter. With the cable open, I'm here. Now with the noise source connected, this is the noise floor I'm served. And I read it out with this thing. And you can see I calibrated it so it shows 0. And now I switch on the current to the noise head. And it is set to now 2 decibels on the low scale. And the noise has increased, of course. And if I read it out, I find by 3.16 dB. That's close enough to 3 dB. I try once more. Well, there is a problem. I have tried to fix it, but so far not successfully. That this readout doesn't always work. It's some issue with the multi-threading. Here we are, 3.1 dB. And that's with the setting 2.1. So the noise figure is close to 2 decibels. I have now connected this signal generator. It's on off and it presents a 50 ohm impedance to the cable to the receive system. And here is the noise floor. I read it out, hopefully. It says minus 0.05. That's close enough to 0. The bandwidth is 1 kilohertz. And now I start this generator at minus 138 dBm. And I have to wait a little to be able to read out here. Well, I have to wait a little more. It says 2.98. So the level increases by 3 decibels when I inject the signal at minus 138 in 1 kilohertz bandwidth. That corresponds to minus 168 in a bandwidth of 1 hertz. That is 6 decibels away from minus 174, which is the Boltzmann constant. So the noise figure according to this is 6 decibels. That's an error of 4 dB as compared to what I saw with the noise figure meter. And the reason is pretty simple. I changed the amplitude to minus 108 dBm. Now the signal is 30 decibels stronger than the noise. So signal plus noise is the same as the signal. And I should expect to see 30 here. But I see 33.7. So this instrument is not accurate at very low signal levels, but the error I see here is 3.7 dB. So rather than having measured 6, I have to subtract 3.7, let's say 4, which means I'm seeing 2 dB. So warning, be careful not to trust things just because they look trustworthy. Maybe if I read the manual I can see that they don't promise so high accuracy at settings above some certain, power settings below some certain level. I have set this generator to produce 30% AM modulation at the same frequency and at a level of minus 117 dBm. I think I can trust the generator down to this level. I have increased the bandwidth to 6 kHz because that is a reasonable bandwidth for air communication. AM voice means the voice bandwidth will be 3 kHz. Then I have taken the signal from the loudspeaker. I have the AGC enabled, and the cable from the loudspeaker goes into this other computer, also running Linrod from the sound card. And you can see the modulation tone here at 1 kHz. And then there is the third overtone of that at 3 kHz, and it's just outside the passband. And I have clicked at 1.5 kHz, and then you can see I have listening only on a 3 kHz bandwidth. So this overtone here is not contributing to the power I'm reading. But I have applied a notch here in the baseband filter to remove the 1 kHz tone. So what I see here is the noise. It is minus 61. And then I remove that notch by putting 0 here, like this. And then the level goes up, of course, because now this carrier comes through. And the level I see is minus 52 to minus 61. That is 9 decibels. So I change by 1 dB to have minus 116 here. And now the noise is at minus 61.8, or yes, minus 61.9. And I again remove that notch and press the right button this time. And now the 1 kHz tone is back. Minus 51.4. This is close enough to 10 dB. I'm not trying to do this with very high precision, which means that a signal of minus 116 dBm is what it takes to produce a 10 dB signal-to-noise ratio on the audio side for a 1 kHz modulated 30% signal. And I press the volt button here. So 0.355 microvolts to give 10 decibels signal to noise ratio in 6 kilohertz bandwidth for the detection of AM corresponds to a noise figure of 2 decibels.